All right, today we're going to be learning a shortcut for finding our derivative. Currently, we have to use the definition to this point, which is rooted in limits. So I would say the limit as h approaches 0 of f of x plus h minus f of x all over h. That's how we would find our derivative. We're going to have a shortcut, develop a shortcut for that today. So we're going to start with the function f of x equals 3. It's a constant function, right? So what does the graph look like? If I graph y equals 3 or f of x equals 3, well, it didn't really pass through 3, but I meant it to. You get a horizontal line that passes through 3. Now, graphically, we've said that the derivative is the slope of the tangent line to the graph at any point. Really, what we mean is it's the slope of the graph at any point. So if I have a graph that's not a line like this, at this point, if I want to know what's the slope of the graph, it's sort of hard to tell what the slope of the graph is there. So what we do when we draw a tangent line, right, is it's a visual representation to see how fast is the graph changing at that point, what direction is it going, and it's really because if we zoomed in far enough, and I can't go in any further in notability, but remember that local linearity idea. If I get really, really close to that point on the graph tends to look like a line anyway, so it's close enough to the tangent line that I could use the tangent line to visualize the slope of the graph. So when I say I draw this horizontal line and I'm asking what's the slope of the tangent line, well, it's how do you draw a tangent line? Because if I take this point here, the tangent line, it doesn't touch the graph just once. It touches it infinite amount of times. So that's just a visual aid to help us understand what it really means, which is slope of the graph at a point. Okay, so that's what derivative means. And on any line, the slope of the graph is constant. So whatever the slope of the line is, that's also the slope of the tangent line, which we really know is the slope of the graph, right? So slope of the graph is the slope of a line. So lines are easy to find the derivative, especially horizontal lines, because the slope of any horizontal line is always going to be 0 at any point. So our rule is going to be if we have, I gotta mute that, sorry. Our rule is going to be if we have f of x equals a constant, any constant, then the derivative is always going to be 0. Okay? So shown below are 3 different polynomial functions. I cut out some examples from my AB notes packet so we can go a little faster here. I'm going to do the derivative. There's a shortcut rule, and I'm going to apply this rule or this algorithm, see if you can figure it out. So I don't have to do the whole limit process. So the derivative of this guy is going to be 6x minus 2 plus 0. Of course, I don't need to show the plus 0. This derivative is going to be negative 15x squared plus 4x minus 3 plus 0. Again, I don't need to show the plus 0. And this derivative is going to be 0, and I'm not going to show that first 0. Then minus 9x squared plus 24x cubed. So what's the rule here? Based on what you saw, how do you think I complete power rule? So first of all, we want to discuss what this thing means. This is an operator. It's telling you to perform an operation. It's saying to take the derivative of whatever's inside here. So it doesn't mean on its own, it doesn't mean, like, I can't write this. I can't say the derivative is 2x because it's the derivative of what? I don't have anything up here. I need like a y to say the derivative of y, or the derivative of f, or if we're doing the derivative of an area function, right? So that would be with respect to radius because it has a radius in it, okay? So without the number up top, this is just an operator. The bottom part tells you, because there's a missing letter up top. I think I just said number. The bottom tells you with respect to what? You're taking the derivative with respect to what variable? So if I was taking the derivative of an area function of a circle, it's got a radius in it. So we're going to take the derivative with respect to r, meaning we're going to treat r as our x, okay? So over here, this is an operator that says take the derivative of this thing in here, since there's nothing up top. So if I put it in brackets, it means take the derivative of the expression in the brackets with respect to x. So treat x as your variable, your independent variable. The rule is you bring the exponent down and make it the coefficient, recopy the base, and then reduce the exponent by 1. All right, so in order to apply this rule, we have to use polynomial type function. Like we can apply it to any polynomial type function. So what does that mean? A polynomial type function will be, well, let's think about what a polynomial is. It's multiple terms. I'm not giving you the official definition, by the way, that are added or subtracted. Okay, and each term has the power of x would have to be a whole number. So while we say polynomial type, this technically is not a polynomial, even though it looks like one, because of this power. But we can still find the derivative of it. So we can apply a power rule to fractional powers. If I made that a negative, that wouldn't be a polynomial. That would also make it not a polynomial. So we can apply power rule to negative powers as well. So it's going to work for all real number powers. So we're going to move on here and actually apply this rule. Okay? The key is we want to leave our answer with no negative or rational exponents. All right? So I can't apply power rule as is. So I've got to bring the x to the numerator and rewrite it in the form, because power rule didn't say anything about when x was in a denominator. So I've got to do a rewrite first. Notice this is f of x. I didn't do the derivative yet. I did some algebra to prep it. Now I can do power rule. I bring the exponent down. I multiply by the 2. I reduce the power by 1. I like to show when it's negative numbers or fractions, I write a little -1 there so I make sure I go in the right direction. Because some people might call it -1. It's actually -3. Then I bring the 3 down and multiply by the -4 to get -12. X, I don't need to show my little -1 because 3 minus 1 is clearly 2. No negative exponents allowed in the answer. So that x goes to the bottom, and it only goes to the bottom of its term. It doesn't go underneath the whole thing. All right, then from here we can get a common denominator and add it together if you wanted to. I would accept that as well. That would turn into this if you're interested in doing that. All right, so for this guy, we have division already. So you have to work on simplifying it and writing it in a polynomial type situation. There's no division here. We can't have this divided by x in a polynomial situation. So what I can do is sort of unadd the fractions. This came from 3 fractions that were added together, and they all had a denominator of x. So it's going to be 3x to the 4th over 3x squared and then 2x. Then I can simplify each one. That's going to be 3x to the 3rd minus 3x minus 2. Notice I did not do the derivative yet. Some algebra to prep it. Now I am doing the derivative. I get 9x squared minus 3. Much easier than doing a limit definition. This one, you've got your multiplication, so it's not in a polynomial type form. So you've got to multiply everything out, turn it into a long polynomial, and then you can apply your power rule to get your answer. We're not going to do that one. This one is the same as that, except that when you simplify, whoops, I'm not doing the derivative yet. When you simplify, you're going to get some negative exponents. So let's look at this one. So it's x to the 3rd over x to the 5th minus 5x squared over x to the 5th. That's going to be equal to, oops, that's an x to the 5th. That's going to be equal to x to the -2. And I have to bring it up. I don't want to leave it as x squared on the bottom because I'm going to apply power rule. Minus 5x to the -3. So then the derivative is going to be -2x. And then I show that little -1, so it's -3. And then plus 15. Subtract 1 off that. It's going to be x to the -4 to the -4. So then I have -2 over x cubed, because I don't want negative exponents in my answer. Okay, this guy here, we don't want, when we have roots, here we have the division, which is a problem, but we also have these roots that we can't have. We have to turn it into a power. So whenever you have roots, I should say, notice that whenever x is in your denominator, it becomes a negative power. whenever x is under a root, it becomes a fractional power. So we're going to call this thing 3x over x to the 2/3. Then to simplify, I can subtract my powers. So if I'm subtracting 2/3, I'm going to make the top 3/3. So I get 3x to the 1/3 up top. So now I can do my derivative. The 1/3 comes down and multiplies by 3 and gives me 1. And then I have x to the, and now when I subtract 1, I'm going to say subtract 3/3. It's a little easier to figure out. So it's negative 2/3. And then what we have to do is no negative exponents. So we're going to put it in the denominator. And then I also don't want rational exponents. So I'm going to write it back in root form. It's going to be x squared, and the third is going to come on the outside. More of the same. We're going to skip it. All right, so these are two trig identities that you have to remember to kind of come up with what's the derivative of sine and what's the derivative of cosine. So two identities we're going to need to prove what this derivative of sine is and what the derivative of cosine is are going to be these identities. If you see cosine of a plus b, that's going to be equal to cosine of a times cosine of b minus sine of a times sine of b. And then for this one, for sine, when we sum two angles, it's going to be sine of a times cosine of b plus cosine of a times sine of b. We're going to use that here to find the derivative of sine. So we don't know what the derivative of sine is. We're going to use this limit rule. And this is why we focused on those famous limits, because you need them to prove the derivative of sine and cosine, so to complete this process. So let's take a look at it. The limit as h goes to 0, f of x plus h means I plug in x plus h into x. So that's why I get sine of x plus h minus f of x, which is just sine of x, all over h. So if I plug in 0, I get 0 over 0 by direct substitution. So we've got to try some algebra to solve this limit, to fill the hole. So the first thing we're going to do is we're going to group this, we're going to use our identity here for sine of x plus h that we just came up with. So we're going to say sine of x times cosine of h plus cosine of x times sine of h. That's what this expands to by that identity before, minus sine of x all over h. Now we've got three terms in the numerator. What we're going to do is we're going to group the first and the last together. We're going to pull those together, so I'll just rewrite that. I'm going to have sine of x times cosine of h minus sine of x plus cosine of x times sine of h all over h. So now I can break this up into two fractions. I can like unadd the fractions. I'm going to stick these two together in one numerator plus this one in the other numerator. So I've got sine of x, and at the same time, I notice that sine of x shows up. Yeah, okay. It shows up in both terms, so I'm going to factor it out. Sine of x. So this term over here is just going to be cosine of h minus 1. And that's that first fraction over h plus, over here I'm going to have cosine of x times sine of h over h. So now I've got here, I can think of this as multiplication of two fractions, and I can pull it apart. The limit as h approaches 0 of sine of x over 1 times cosine of h minus 1 over h. There's our famous limit. Plus over here, I'm going to pull that apart into two fractions times each other. So I'm going to say cosine of x times over 1 times sine of h over h. There's our other famous limit. So now I know if I do direct substitution here, sine of 0 is 1, so I get 1 over, sine of 0 is 0, so I get 0 over 1 times, this is a famous limit. Wait, what am I doing? I'm sorry. Start over. This has an x in it, so I don't plug anything into it. I'm plugging 0 in for h only. So I get sine of x. And then this is our famous limit, which is 0 when I plug 0 in for h, plus cosine of x over 1 is cosine of x, because I'm plugging 0 in for h, times If I plug in 0 for h, this is our famous limit, so we get 1. So this ends up being cosine of x. So the derivative is cosine of x. Okay. A similar proof would apply over here. I'm not going to do it out for you. The derivative is going to be negative sine of x. You can work through that on your own if you like. So the derivative of sine is cosine. These are just rules we're going to have to memorize. Derivative of cosine is negative sine. Notice I call these the cofunctions. Notice the derivative of the cofunction is negative. Okay, so you can remember that sine is, the derivative of sine is cosine, and the derivative of cosine is sine, but the cofunction derivative becomes negative. Hi. All right, so for each of the following functions, find the equation. So we're going to work with this rule for our derivatives of sine and cosine. So let's see here. The derivative, we can go one term at a time. So this is going to be the derivative of 2 theta. You can treat theta like your x is going to be 2. So we're starting with the derivative here to find the slope of the tangent line, by the way. So it's 2, and then plus. The derivative cosine is negative sine, and 3 is a constant, so it just comes along for the ride. So that plus actually turns into a negative because cosine turns into negative sine for the derivative. 3 comes along for the ride, and we have sine of theta. So let me show you what I mean there. Again, it goes back to our properties. If I want to find the derivative of 3 times a function, because the derivative is rooted in limits, the properties of limits apply. So I have 3 times the derivative of f, which means that would be equal to 3 times f prime of x. So constants, I just say, come along for the ride. All right, so that is our derivative. So now they want us to write the equation of the tangent line. So first we figure out the point of tangency. That's going to be g of pi. So when we plug it into the function itself, we get the y value. That's going to turn out to be 2 pi minus 3. Then for the slope of the tangent line, we plug our target x value into the derivative. Again, this is our target. They're saying at pi. So if I plug pi into the derivative, I'm going to get 2. So then to write the equation of the tangent line, it's going to be y minus the y value. It's got to be in parentheses because you've got to distribute that negative. Y minus the y value equals the slope times x minus the x value. I could leave it like this, or if you want to simplify it, you can. In this case, it may be helpful because if I try to put it into slope-intercept form, I get y minus 2 pi plus 3 equals 2x minus 2 pi. You notice those pi's will go away, and we'll get y equals 2x minus 3. So in this case, it's probably helpful to simplify. All right, so in this guy, we're going to take the derivative because we're going to need it to find the slope of the tangent line. The derivative of sine is cosine, and 4, the constant, comes along for the ride. Theta is like an x. The derivative of theta is just 1. So then I'm going to do the point of tangency is going to be f of pi over 2. And that is going to work out to be sine of pi over 2. So that's going to be 4 minus pi over 2. And then our slope of our tangent line, I'm going to do f prime of pi over 2. That is going to work out to be negative 1 when I plug it into the derivative. So again, I've got y minus the y value, and then the slope times x minus the x value. You simplify that like we did earlier, and you get this. You can pause the video at any of these points where I'm plugging stuff in and just saying what the answer is. I've clearly kind of worked it out ahead of time already. I'm trying to cut minutes off the video on stuff I don't think we need. If you need to practice doing that, you should do it. Like if you're not sure about your trig values when I plug in an angle, you need to practice that. You need to pause the video and get ahead of me and see if you get it right. All right, let's move on here. Okay, so now we're going to tie this in with some other stuff that we were learning about. So if you're given the equation of a function, how might you determine the values at which the function has a horizontal tangent? So a horizontal tangent, remember that means that f prime, whoops, I should use, I don't like capital F here, f prime of x equals 0. All right, so if f of x has a horizontal tangent, then f prime of x equals 0. So what we're going to do is find f prime of x, set it equal to 0, and solve. Now remember, when we have a horizontal tangent, it usually happens or can happen when there's a maximum, but just because the tangent is horizontal doesn't mean there's a maximum. And we'll see that in these examples here, in one of these examples. All right, so at what values will this function have a horizontal tangent? So first I find the derivative. The derivative is 3x squared plus 1. I set the derivative equal to 0 and solve for x. I subtract 1, I divide by 3. I square root. There are no real solutions, right? So, because that's undefined. So no solutions. So what you say is the graph of f of x is always increasing. We don't really need to add that part because they didn't ask about that, but I wanted to point that out because the derivative is always positive. This, no matter what x I plug into it, will always be positive, right? If I plug in an x, no matter what I get, when I square it, it's positive times a positive 3 plus 1 is always positive because we know that f prime of x will be positive for all x. So that's not what the question asked. I just wanted to point that out as well. To answer the question, you would say f prime, it has no horizontal tangents because f prime of x is never equal to 0. So I would say no horizontal tangents because f prime of x never equals 0. That's how I'd answer that question. All right, let's move on to the next one. Oh, I wanted to show you what that looks like. So this is the graph. I put it in. The orange is the graph, and here's my tangent lines as I go along the curve. See, it never gets horizontal. It starts to bend back here, but doesn't bend enough. The graph keeps increasing the whole time, as we said before. So at what values does that function have a horizontal tangent on the interval 0 to 2 pi? So let's do our derivative. The derivative of theta is 1. The derivative of sine theta is cosine theta. So now we want to set that equal to 0. Oops. So when does the cosine of theta, oh my gosh, I'm struggling. When does the cosine of theta equal negative 1 on the interval 0 to 2 pi? That's going to be when theta is equal to pi. So then we're going to say that at what values? So we'll say it has, and we'll explain. So we'll say f of theta has a horizontal, I know I didn't ask to justify, but we're just practicing. F of theta has a horizontal tangent line at theta equals pi because f prime of theta is equal to 0 at theta equals pi. Let's take a look at that. I have that one graphed for you. So here's our tangent line of that function. And you can see we're only talking about from 0 to 3.14. So it becomes tangent right there. And becomes horizontal right there. And notice that, like I said before, typically we think of a horizontal tangent line only happening at a high point or a low point, like a maximum or a minimum. It can happen even if the function keeps increasing or decreasing. So that happens here, and it actually happens over and over because we know sine functions are cyclical. So I get a horizontal here, but that's just outside the interval they were asking for. And of course, it keeps going. We'd get 1 at every one of those little steps. And yeah, we're done with those notes. Nice. They're getting shorter.